Hi, welcome to this particular module, and in this module what we will see, we will continue with the previous module in which we had talked about photoresist, and we will continue on lithography, and then we will take one example to help you out how to fabricate a EEG electrode or a metal electrode on an oxidized silicon substrate. You can also use instead of oxidized silicon substrate, you can use glass, you can use polymer, and there are different substrates are available on which you can design this particular electrode. Now continuing to our last topic, I told about the mask, right, and I have shown you a bright field mask and dark field mask. So the one that I am holding right now in my hand is a bright field mask, as you cannot see. So I will put on my a background as my shirt, and you are able to now see the glass that I am holding, which is a 5-inch glass, and there is some pattern on glass, right. So this is, you see, most of the part is transparent, and only the pattern which is here in the center, it is dark, right. So the field is bright and pattern is dark. This is a bright field mask, bright field mask. This is what we were talking about. You have a chrome glass or chrome mask on which there is a pattern and the field is bright, bright field mask. But if you have something like this, which I am again holding, you can very clearly see that this is a dark field mask, and only two places you will be able to see that there are two holes here and here, right, here and here. So you can see here, right. There are two transparent area, while the majority of the area, majority of the field is dark, because everywhere there is chrome except these two holes. So this is your dark field mask. It is very clear to understand and very easy to recognize a bright field versus dark field mask. And importance of bright field versus dark field mask we will discuss when we talk about how to take out the contacts from the electrodes. I will teach you about that particular part. So coming back to the photoresist, if you see the screen, we were talking about positive and negative photoresist, and we also discussed that in positive photoresist the exposure or exposed area will become weaker and unexposed area will become stronger. In case of positive photoresist, the unexposed region will become stronger. So this is an example that if you have a bright field mask which is shown here with a pattern that shows like plus, and if you use positive photoresist, then the unexposed area would be stronger, and you can see here that the unexposed area is stronger, while the exposed area, which is this area, gets weaker in case of positive photoresist. When you use positive photoresist with bright field mask, this is what will happen. You use positive photoresist with bright field or dark field, does not matter. The concept that you need to remember is that the unexposed region would be stronger. Now if you take a negative photoresist, what will happen? The unexposed region is weaker. See, the unexposed region of the mask in case of negative photoresist will be weaker, and the exposed region, which is this region, will be stronger. You can see here the photoresist is intact in this region. In this case, the photoresist is etched from the area which is exposed, and the photoresist is intact in the area which is not exposed. Alright. Same thing is done in this sentence, that exposure to UV light removes resist, that is positive photoresist. You see exposure of UV light, exposure of UV light will be in this area, here, wherever it is bright field, right. So the exposure of UV light will remove the photoresist when we talk about positive, and when we talk about negative photoresist, then exposure to UV light will retain the photoresist, right. See, it is retaining the photoresist, same thing, right. So different authors write in a different manner. Some will write that unexposed region of the in case of positive photoresist will become stronger, in case of negative photoresist unexposed region will become weaker. Some people will write that exposed region in case of positive photoresist will become weaker, and exposed region in case of negative photoresist will become stronger. Some people will write that exposure to UV light removes resist in case of positive, exposure to UV light retains photoresist in case of negative. The point remains same. Okay. So, now if you see the illustration of positive and negative photoresist, even though this overall the schematic is small, still you will be able to understand. See, you start with a substrate. So, this is my first step, then of course, you clean the substrate, that is but obvious, okay? You need to follow it. Second is that you are applying a photoresist resist film. Third one is you use a mask. This is second where photoresist is applied. Third one is use a mask. Now, if it is positive, you can see the mask pattern is something like this, it comes out like this, and then there is a one line here, alright, and this area that we are showing is dark, which is some pattern is there like this. Okay. This is our mask pattern, which is this one, alright. Now, if the photoresist that you have spin coated, which is this one, alright. So, what will happen? First is your substrate, second is you spin coat photoresist, then perform soft lithograph, soft baking, which is at 90 degree centigrade 1 minute on hot plate. Then you load the mask. If the mask pattern is as shown in schematic, then if you use positive photoresist, you will retain the area which is not exposed, and the exposed region will be etched, and finally, you have to what you can do, you have to hard bake it before you develop the wafer. So, after you develop the wafer and then you can hard bake it. So, the point is you go for photoresist coating, then soft bake, then expose, then develop, and then hard bake. Hard bake is done at 120 degree centigrade for 1 minute on hot plate, and then you can etch or strip the photoresist by dipping the wafer in acetone, by dipping this wafer in acetone. Now, this is case of when the photoresist is positive, but if the photoresist is negative, what will happen? Again you have to coat the photoresist, soft bake, load the mask, expose the wafer, then develop the wafer. In this case, when you develop the wafer, you will see that the unexposed region becomes stronger, and the exposed region unexposed region will become weaker, and the exposed region will become stronger, right. This is what you can see here, and then what you have to do, again you have to perform after developing hard bake. After hard bake, you have to dip the wafer in acetone. So, if you dip this wafer in acetone, then you will achieve this pattern, right. So, this is how positive and negative photoresist works, but the point is how you will coat or coat the photoresist onto the wafer, and you have seen the wafer in the previous modules, silicon wafer and oxidized silicon wafer. So, you have to first take the wafer, clean it and rinse it, right, which is washing step, and then you load the wafer onto the vacuum chuck, which is here, and then there is a spindle which is connected, this whole chuck is connected to vacuum pump, and your wafer is loaded onto this vacuum chuck, is loaded, it actually makes a hard contact. Okay. So, now the wafer is holded, this is just for you to understand that there is a gap which is shown, actually there is no gap, it is just to show you that there is a hole which will, through which the vacuum will be generated, and this and also these lines are there through which the vacuum will be generated. This will help the wafer to stick to the vacuum chuck, and then there is a spindle which will rotate. So, when you load the wafer, the photoresist is dispensed, and initially it is at a slow RPM to have a uniform deposition, followed by the thickness that you want. As you can see here, that if you increase the spin speed, that is rotations per minute of this particular spindle, what will happen? The rotations per minute increase means the thickness is decreasing. As you increase the rotation, the thickness would decrease, as you decrease the rotation, the thickness would increase. Now, here the chart is showing for different material, which is SU8 material. SU8 is another negative photoresist, we will discuss about SU8 at some point of time, and depending on the viscosity, we have a different thickness of SU8 pattern is possible. So, here let us see that what is the characteristics of photoresist, the properties, that it should have a high etch resistance and good adhesion. So, it should stick well to the wafer. The second one is the wafer is held onto the vacuum, the photoresist is dispensed on the substrate. It can be silicon, it can be oxidized silicon, it can be glass, it can be polymer. Then there is a slow spin at 500 rpm to have a uniform deposition or uniform spreading. Finally, we have to ramp the spin coater from 500 all the way to 5000. It depends on what kind of thickness you desire. Photoresist is spin coated or spreaded by centrifugal force, and the quality that we need to measure are time, speed, thickness, uniformity and particles as well as defects. So, the particle defects would be there if the photoresist is not clean. That is why we require a clean room, we require particular protocol to follow, so that to have a clean photoresist. And you can very clearly see that the spin speed or thickness is inversely proportional to the square root of spin speed. You can also further see that the higher viscous photoresist coated with lesser thickness, while higher spin speed will result in a higher thickness of the photoresist. Then we talk about, so if you recall what we said, that in photolithography the first step is you take a substrate and then perform washing of wafer, right. Then second step is spin coat of photoresist. Third step is soft bake, right. So, and then fourth step is the mask loading and UV exposure, right. Fifth step would be developer. Sixth step would be hard bake. Let me write down. Right. And finally, after you do this step, you have to etch if there is some metal, and if you want to remove this or strip the photoresist, you can go for acetone. So, these are the steps. So, why we require soft bake? So, this slide shows the reason of using soft bake. First is that it will help in partial evaporation of the photoresist. You see, so photoresist comes in a semi solid or in a liquid form, and it will get solidified only when you bake it, otherwise it will stick to the wafer. So, or to the mask, right. This photoresist is on the substrate, let us say it is on oxidized silicon substrate and photoresist is there. So, if you load the mask on this substrate, what will happen? It will stick to the mask, right. To avoid this thing, what we do? We have to soft bake the photoresist, that is one reason. Second is it will improve the adhesion, then it will improve the uniformity, it improves etch resistance. Finally, it helps in optimizing the light absorbance, because the photoresist is a photo effect. The effect of photons on the photoresist will be tremendous, because that is what it is meant for. So, it is, if you do not bake it properly, then the absorbance would be different and you will not get the pattern. That is why you need to soft bake the photoresist. Then if you see the next slide, you will see on the exposure. So, how exposure occurs? If somebody wants to go in detail of optics related to the exposure, we can go about that. However, my interest of this particular module is not to go in detail on the optics, but rather than just to give you the flavor of the lithography, and then we will use we will show you the use cases for using the photolithography in neuroscience or neuroinstrumentation. So, the exposure is on the wafer coated with photoresist is via mask, and there is a UV light source, right. So, same thing is shown here, that there is a strayed reflected light, right, and then there is a lens, and reflected light is collected by the lens, which is finally deflected and focused by the lens onto the substrate. So, when light passes through the mask, this is a dark field mask, and you can see here the light can pass through this region. When it passes through this region, what will happen, that depending on the distance between the wafer and the mask, the way the reflected light collected by the lens would be different, and ideal pattern is here, but practically we get something around this one. Okay. So, again it depends on what is the dose of the UV exposure onto the photoresist. It depends on what kind of substrate and photoresist you use. For example, if you use silicon, then the relative dose would be 1 times, that is 1x, you do not have to increase the dose, while if you use glass, Pyrex or ITO, ITO is indium tin oxide, is a semiconducting oxide, then you have to go for 1.5x. But if you go for silicon nitride, which is an insulator, or gold aluminum, which is a conductor, in fact nickel, copper and titanium, which are also conducting materials, then you have to increase the dosing by 1.5, or you can keep it 1.5 to 2x. So, that is the requirement for the dosing. Dosing is the amount of dosage given to or from the UV source to the wafer. So, when you talk about development, see development, there are two ways of developing. One is the using the photoresist. So, negative photoresist has a different developer, positive photoresist has a different developer. So, what I meant is not two ways of developing, but in fact we have two different developers, positive for positive photoresist and for negative photoresist. So, the soluble areas of photoresist are dissolved by developer chemical, and visible patterns appear on the wafer either in terms of windows or in terms of island. You can see the schematic here. When you have overdevelopment, you will see the schematic where instead of, this is an ideal case or normal development. Now, for all the other cases you will see, if it is incomplete development, when this occurs, when the time for the photoresist etching or developing is let us say 1 minute, and somebody or someone in the lab is impatient, and he or she will remove the wafer in 50 seconds, then the photoresist is not completely developed. Okay. Then the second case will be if the photoresist time is 1 minute, but someone takes it further like more than 2 minutes or 3 minutes, then there is a over development. And same thing will occur that if it is optimization is not taken care of about the dose and exposure, then there can be under development. So, there will be under development, incomplete development and over development in case of the photoresist be depending on photoresist developer and the exposure time. So, these are all called recipes, so that the time is optimized, the photoresist quality is optimized, the spin coating speed is optimized and other things. So, again you take an example of a substrate which is coated by photoresist, this is a mask. So, what will happen if it is a positive photoresist, the unexposed region will become stronger, you can see here, right. Then unexposed region is becoming stronger, but if it is a negative photoresist, then the unexposed region will become weaker and the exposed region will become stronger, correct, easy. So, you have to understand this this particular parameter or properties. Now, if somebody is interested in the chemistry, we are not right now. So, do not worry about this what is the polymer and what are the chemicals that are used to develop this polymer or to have the polymer, but our main interest is that the function of the resist primarily is to have a precise pattern formation and protection of substrate during etch. That is our two parameters that photoresist should always adhere to, and then other parameters can be categorized as optical properties, that is resolution should be proper, its photosensitivity should be proper, index of refraction should be there, and if you talk about from chemical and mechanical properties of the photoresist, then there are some other parameters like etch resistance, it should be thermally conductive, it should be not too sensitive to ambient, and it should have a good adhesion, its viscosity should be uniform, and finally contamination safety related properties we can determine, which are particle counts, metal content and flash point, and the ingredients in the eye line photoresist are here, we do not have to worry about it. So, the point is, if I go over quickly about telling you about the etch resistance, right, substrate, protection of substrate, these are two important parameters, all right. This is precise pattern formation, protection of substrate during etch. So, let me just give a quick example of how you will protect the substrate during etch. So, what it means by is that if I have a pattern of photoresist, and let us say this is silicon dioxide, okay, and I have my photoresist pattern after doing lithography, and this is my photoresist. What is this one? Silicon dioxide, my substrate is silicon, and I have some photoresist, positive or negative, does not matter. After I perform hard bake, I want to etch silicon dioxide from the area which is not protected by the photoresist. You can see this area which is not protected by photoresist. So, I want to etch silicon dioxide. So, let us etch it. So, if I dip this wafer in BHF, buffer hydrofluoric acid, the silicon dioxide from the area which was not protected by the photoresist will get etched. That means, I will have silicon dioxide only in this area which is protected by photoresist, correct. But that does not mean the protection of substrate. The protection of substrate means that during this thing, right, the for photoresist, silicon dioxide is now a substrate, right, silicon is not, silicon substrate is there for silicon dioxide. So, the one layer below is the silicon dioxide. So, photoresist in this case will protect the silicon dioxide from over etching. If your time is maintained, that means recipe is maintained, the photoresist should not affect the substrate below it, that is what it means. Further you go for G line and I line resist, then there is further chemistry, let us not worry about this one, but generally you understand that the organic polymers that are spun onto the wafers and pre-baked to produce a film about 0.5 to 1 micrometer thickness. This is the thickness generally we use when we take the photoresist. So, about the material parameter, the average energy of UV source is less than that of visible range. So, to maintain dose, chemically amplified photoresist can improve the efficiency. We can also use photo acid generator is converted generally to an acid by photon exposure, and later in a post exposure bake the acid molecule reacts with blocking molecule onto polymer chain, making it soluble in developer. So, this is what is the chemistry behind it. That means that when you expose the photoresist, what will happen. So, initially the photo acid generator will convert this is converted to an acid by photon exposure, which is a UV light exposure, and later on this exposure when we do a post exposure bake, then this acid molecule will react with a blocking molecule onto a polymer chain, and thus making it a soluble in the developing material. We do not have to worry about it. Okay, I am just this is just an concept of how the photoresist actually changes its properties when it is exposed to UV light. And finally, if there is a cross linking of resins helps in hardening, that means in case of positive photoresist, the unexposed area, the cross linking will occur and it will harden the photoresist. In the case of negative photoresist, the unexposed region will be weaker and it will reduce it or soften the photoresist. So, if you talk about basics of mask, then you need to understand a few things. That the first is that layout file, that is how you will design this mask that I was showing you on my in the introduction of this module, is the first you have to design the pattern using Clavin, and this is given to a mask developer. Then beam scans and blank mask are used. Or actually the blank mask is a mask coated with the photosensitive material, and then beam scans are used to expose as per the pattern that we want. Finally, the mask material can be a glass plate with chromium, which I have shown it to you, or sometime it is also called chrome mask. So, the chromium mask that I was showing it to you, this is a glass plate, right, on which there is a chrome pattern. So, this is also called chrome mask, it is also called chroma because the pattern is with chrome, that is what it is saying. Then if you see that there is another way, e beam selective pattern the mask develop the resist and remove chrome from the desired area. So, that is the scanning is done by electron beam and it is selective for the pattern that we require. Finally, mask making should be done with a great accuracy. Mask must be extremely clean because any defect will result in the incorrect feature in all the devices or the chips. Finally, a mask is usually 5 to 10 times larger than actual feature size. The features are reduced or zoom out during lithographic process. So, it will called as a 5x or 10x mask. In addition to design, mask will have alignment marks and test structures, we will discuss in one of the module. But if you see this particular slide, what you see is that if you take the photo mask, then photo mask can be developed or the mask can be developed using Fe2O3 on soda lime glass, or it can be chrome pattern on glass. There are two types, bright field which mostly transparent, features will be opaque, and dark field mostly opaque, features will be transparent. These are the patterns which are used for alignment mark. We will talk about alignment mark when we take a use case, but there are some defects in the photo mask. You have to understand, first is a chrome defect, you can see here, which is called chrome spot. Then in some cases there is a extension of the chrome, in some cases there is a bridging, see the extension of, now how this defect will happen, or how this defect will affect the device performance. You see, in this particular area you can have thousands of transistors in reality. So, when you talk about transistors and other devices, then this area you are killing that many number of transistors, that is why this chrome spot is not okay. Same thing goes for chrome extension. Let us take not an example of a transistor, even we take example of just a heater. And heater, what is heater? It is a, let us say there is a, this is a heater, okay. Let us say this is the heater pattern. And what you see here is a chrome extension. So, for this one my R equals to rho L by A, that will be my resistance, where R equals to resistance and rho is resistivity, L is length, A is area. But if I have a chrome extension which you can see here like this, right, then my calculation will not come correctly, right, it will affect the overall resistance of the heater. Then if you, the another defect in the photo mask is a bridging defect. What is bridging? So, in this case let us say this is a heater and there is a short between two lines, right. So, it will short the lines. So, the resistance that we were calculating will not be accurate because there is a short between the two lines. Then there is a spot, that means that if you see a spot, how will it affect? It is like this, there is a heater and there is a spot, okay. If this is a spot, let us say there is a spot in the, so let me show you in a different way, so it will help you out. If I only zoom this area, okay. So, if I zoom this area, it will look like this, it is a chrome mask. So, everywhere there will be chrome, right, everywhere there is the chrome, and there is a spot, chrome spot, or actually it is not called chrome spot, it is called pinhole, right, pinhole. So, what will happen? This pinhole will not have any metal is not there in the pinhole, right. If metal is not there in the pinhole, my resistance value again would be affected, you got it. That is why pinhole is not also okay when you take out when you look at the photo mask. Then there is a clear extension, that means that in this case what we will see? We will see that this line is broken to an extent. How I can show it to you? Let me just show it to you here. Let us again zoom this version, okay, and what will happen is like this. So, now again you see that the resistance of this line, right, would be different because there is a clear extension, it is a clear breakage, right, it is a clear breakage of the metal. So, here the resistance will be different. Finally, there is a clear break is absolutely not allowed because it will just not help us when you talk about heater. Clear break means like this pattern. So, if I measure resistance of this particular heater, as I connect with a resistance meter, what will be resistance? Resistance would be infinite. Why? Because there is a clear break in this particular pattern. So, these are some of the defects that occurs in the photo mask. So, before you start using the photo mask, you should know these defects, namely 6: chrome spot, chrome extension, chrome bridging, pinhole, clear extension and clear break. So, lithography sequence is again shown here. You take a wafer, you wash the wafer and then you do the pre-baking step, then you coat the photoresist which is your positive or negative photoresist, then you go for soft bake or pre-bake, both are okay. You see this pre-bake, some people use pre-bake, some people use soft bake, some people use post exposure bake, some people use hard bake, depends, okay, and which kind of photoresist you are using, that is also another point. So, if you use SU8 photoresist, then this is the correct sequence that is showing here. So, in generally what will happen in positive and negative photoresist, the sequence is that you coat the photoresist, then go for soft bake, then you load the mask and perform UV exposure, then you develop it, then you go for hard bake. Hard bake is also called post exposure bake. Soft bake is also called pre exposure bake, or it is also called pre bake. Pre bake is short form of pre exposure bake. This is post exposure bake PEB. And then finally, after hard bake, develop a hard bake, and then you go for the next step. This is in case of positive and negative photoresist. But in case of SU8, what will happen? You spin coat photoresist, which is your SU8 in this case, then you perform soft bake or pre exposure bake, pre bake, then you load the mask, perform UV exposure, then you perform post exposure bake or hard bake, post exposure bake or hard bake, then you perform developing step. You see what is the difference? Here first after the exposure you have to develop, and in this case after exposure you have to go for post exposure bake, fine, and then develop. So, only one step is interchange. So, this case, this sequence of soft lithography of the lithography is for SU8. As you can see here that after coating there is a pre bake, then there is a exposure of UV light via mask, and then there is a post exposure bake. After post exposure bake you have to develop the wafer. After developing the wafer you can check it about the structure or the pattern that you get on the wafer.